Well, good morning and welcome to this webinar. What I'm going to be talking about today is how we can use Java to build the Internet of Things. And I'm going to talk about Java in all different aspects of the Internet of Things, from the edge, where we have our devices, all the way through to the cloud, and specifically how we can leverage open source to help us develop these types of applications. So to start with, let's talk a little bit about what we mean by the Internet of Things. And if you look at the history of this, I can actually remember being involved in some of this work a number of years ago when I worked for Sun Microsystems, and there was a project that was called Smart Dust. And the idea behind this was to have very, very small sensors that could be battery powered or powered by solar energy or even gathering energy from movement or something like that. But the idea was that these could be distributed in anywhere that you wanted. You could throw them into a field, you could throw them out of the back of a plane or whatever, and you could then gather information from these, and they would form their own kind of mesh network. A lot of the ideas behind this also came from RFID, radio frequency identity, and that was more about the idea of giving everything an identity so that you could identify it remotely. And RFID tags were not powered, so you would use a radio transmitter. You would then activate the tag and read back the information. Now, what that's kind of morphed into now with what we traditionally talk about IoT today is network connectivity. So we're still talking about having devices connected, but it's more the traditional kind of network that we're used to. So we're using IP, we're using IPv4, IPv6 to give us a larger range of addresses, but even using name address translation, so hiding things behind a firewall so we can allocate IP addresses behind a particular gateway or something. But also using URIs, Universal Resource Identifiers, and this kind of comes back to some of the technology we can use in terms of web interfaces and so on. So this is kind of the history behind the Internet of Things. What we've also seen is a shift in terms of where people want to apply the Internet of Things. Where do they want to apply this ability to gather data? Where do they want this ability to be able to control things in a much finer grained way? And one of the big areas that IoT has been very successful in is the idea of the industrial Internet of Things. What we're doing there is using sensor data, using actuators in more industrial scenarios, so chemical engineering plants, generators, nuclear power station, these sorts of things. And there's a lot of technologies around that which make it very useful to be able to build these types of applications. So the idea of machine-to-machine interaction. So we're not having machine-to-person, person-to-machine type thing. It's just machines talking to each other. Definitely big data, generating lots of information, and then applying some of the newer technologies, things like machine learning, deep learning, to that, to be able to extract out of that useful information, to be able to predict what's going to happen in the future based on what happened in the past. And this is really the development of what are now becoming called smart machines. Now, if we look at a typical IoT architecture, really what we're dealing with is three different tiers. But not in the sort of traditional client-server type of way of doing things. So this sort of diagram here shows what I mean by those three tiers. We need our sensors and our actuators, the things that are going to gather data, the things that are going to enable us to control things remotely from the information that we're gathering. So we have sensors and actuators, and these are going to be the things that have a small amount of processing power but network connectivity. Now, the thing with having lots of sensors and lots of actuators is it means that you're dealing with lots of data. And rather than having every sensor sending that data to the cloud to be analyzed and stored and processed, what we need to do is to have some way of collating that information, filtering that information before it gets passed to the cloud. Because in its raw form, it may not be as useful as if we do some pre-processing on it. And that's where we see the idea of IoT gateways coming in. So we've got a concentrator that talks to a number of sensors, gathers data from that, filters it, collates the information, and then passes the aggregate information onto the cloud. So that we're not having to pass every single piece of data to the cloud in order to have the information processed. And then obviously we've got our cloud, our data center that somebody else is running for us, and that can do the important things of analyzing that data that comes from the gateways, making sense of what the sensors are telling us, and then making decisions on what we want to be able to do with that data, sending that information back to the gateways who can then use it to tell the actuators, this is what we want to change. Also, in terms of the cloud, we can store the data so that we can have a historical record of what's been going on, either for auditing purposes or simply for tracking things over a period of time. So this is the kind of thing we're dealing with. We're dealing with three distinct areas of our architecture: sensors, gateways, and the cloud. Now, if we look at how we can develop these types of things, one of the things we need to look at is the reality of Moore's law. Now, I'm sure everybody has heard of Moore's law. Moore's law was created by Gordon Moore, who was one of the co-founders of Intel. And back in 1965, that's over 50 years ago, I know that because I was born in 1965, over 50 years ago, Gordon Moore predicted that the density of transistors on a chip would double roughly every 24 months. It's kind of changed a bit. I mean, some people say 24 months, some people say 18 months, but we can say roughly 24 months is the time it takes to double the density of transistors on a chip. What people have seen that as being is a law, which is more of a rule of thumb really, that the processing power that we have available to us doubles every 24 months. So every 2 years, we're doubling the amount of processing power that we have. And this has held true for a long time. And it seems to be that we will be able to continue this at least for some time into the future. Now, if we look at the inverse of Moore's law says we can squeeze more transistors into the same space. But that also means that the cost of producing processors and having connectivity has decreased as well. If we use an example of that, this is the IBM 5150. This was really the first IBM PC, the first personal computer that was launched for commercial use, 1981. And this had an Intel 8088 in it. That's an 8-bit processor running at a whopping 5 megahertz. And in terms of memory, that had something between 16 and 256 kilobytes of RAM. And that is kilobytes, not megabytes, not gigabytes, but kilobytes. And because I'm old enough to remember some of this, I can remember that you can actually do quite a lot in literally 16 or 32 kilobytes of RAM. You really can. You have to be quite dedicated to squeezing things into that space, but you can be very clever and get things to work in that kind of memory. But if we look at what that cost, if we adjust the cost forward to today's numbers, that would be about $4,500. $4,500 for an 8-bit processor and, let's say, 32 or 64 kilobytes of memory. Let's compare that to what we have today. Let's take a very good example, which is the Raspberry Pi Zero. Now, this has been around for sort of about a year, 18 months, I think. And what that does is provide you with pretty much an IBM PC. Okay, you don't have the keyboard, you don't have the monitor, but in terms of the internals, you've got pretty much the same thing that you have in an IBM PC or from 1981, except that this uses an ARM v6 processor. Now, that's a little bit of an older processor, but it still will clock at 1 gigahertz. That's 200 times faster than the IBM PC of 1981. It also has 32-bit address bus, which means you've got 4 times as many bits as your IBM PC. And in terms of memory, it has 512 megabytes of RAM, which clearly we look at and we think, well, that's quite a small amount by today's standards, but it is still 2,000 times more than we had in the IBM PC. What this costs today is $5, and that's the retail cost. So that's what you buy it for off the shelf. In terms of what it costs, it's less than $5. So the reality is that processing power now is very much cheaper than it used to be. It's got to the point where we don't even need to think about it. So when we're talking about the edge and our devices, we can actually put processing power in there, the cost of which is negligible, because we can say, well, it's going to cost us couple of dollars to add computing power and network connectivity to whatever it is we want to add it to. So processing network, the cost is negligible. We don't need to concern ourselves with that. The other thing that we've seen a big shift towards is cloud computing, moving away from having our own data center to using something like Amazon Web Services, Microsoft Azure, Google Cloud, whatever. And this gives us the perception of having really limitless computing power. We simply pay for what we need, and the more we need, the more we get. It's a bit like using electricity. You want to use more electricity, you plug things in and it draws more electricity. You simply pay for what you use for. So from a hardware perspective, what we're dealing with here is the fact that we can add connectivity, we can add processing power to every single device we want to. We have the storage, we have the processing in the cloud that we can use to take that information, analyze it, predict what's going to happen, and then use it in an interesting way. But this is only half the problem. Having the hardware available to us is a start to a solution. But how do we then develop the software that's going to enable us to collect this information, analyze it, and then use it? That's what we need to look at for the rest of this webinar. So I'd like to pause here and just have a quick poll question for the people who are on the line. And I'd like to ask people, what size of IoT project are you planning or are you developing? And I've given you 4 different answers. So small, which we're talking about sort of tens of edge devices, tens of sensors, maybe gigabytes of data, possibly megabytes of data. Medium, where you're talking about thousands of edge devices, possibly terabytes of data. Large, where you're talking about hundreds of thousands of devices, maybe petabytes of data. And even larger, billions, trillions of devices, yottabytes of data. So click on which one is relevant to you. And I'll just give a few seconds for people to do that. And then I will ask for the results of the poll. Hopefully I will see in a moment. I don't see the results, so maybe I'll have a look at the results at the end. Oh, there we go. Okay, so most people, it looks like, are doing small projects, and we've got a couple of people who are doing large projects. Okay, so that's interesting. But it seems that most people are dealing with smaller projects. Okay, so we'll go back to the slides, and now we'll talk about the challenges and solutions. The way that I've done this is I've looked at it from the perspective of these 3 different tiers that we have in our Internet of Things architecture. So we have cloud, we have gateways, and we have edge devices, sensors and actuators. And what I'm going to do is I'm going to go through a number of challenges that we have and how we can provide a solution to that using Java and open source technologies. And as you'll see as I go through the slides, what I've done is highlight which of these tiers are applicable in terms of the specific challenge. So the first one, and this applies only to the edge devices, is how do we interface to the sensors and the actuators that we're going to be working with. This has always been something of an issue because there are a number of different ways of doing this. So you have things like the I2C bus, the integrated circuit bus. Then there's an alternative, which is the SPI, the serial peripheral interface bus. And these use different ways of communicating. So in the case of I2C, you've got 3 lines. In this case of SPI, you've got 4 lines, which have, in the case of SPI, you've got a clock versus I2C, you're just sending signals. And then there's the idea of serial interfaces. So good old RS-232, RS-423, USB, things like that. They're still very much used in a lot of different places. And then you've got lower level things like direct memory access. But clearly one of the challenges we have is how do we write code that can interface through these types of things? And the answer in terms of Java is libraries. And so there are a number of very useful libraries that are available, mostly open source, mostly free, that you can use to simplify the development of interfacing code. So if you need to get down into the sort of lower level sort of weeds of the interface, then you can use JNI, Java Native Interface. That will allow you to write some native code which talks directly through something like DMA, and then you can wrap it in a Java wrapper and expose it as a Java API. But for things like SPI, things like I2C and UARTs, there are libraries already available. If you're using something like the Raspberry Pi, there is a nice open source library called Py4j. What that will do is provide you with a set of standard Java classes which allow you to say, right, I want to talk to this particular I2C device. It has this address. I'm going to send this information to it. I want to read this information back. That type of thing. It makes it just a simple Java interface. You don't have to do any complex bit twiddling or addressing of specific things. There's also a thing called the Device I/O library. This was originally part of the Java Micro Edition, but has now been ported to Java SE. So if you want to use the Java Standard Edition, then there's a Device I/O library available, which again is like the Py4j, but being more generic rather than for the specific Raspberry Pi board. So the idea is to give you a higher level abstraction. This makes it simpler to code, simpler to develop your application, so you can do it more quickly. You don't need quite so many skills to be able to do that. Next thing is porting. And what we see here is for things like edge devices, for things like gateways, if you want to move to a new hardware platform, then you need to port your application to that new hardware platform. That means you need to take your application code, you need to look through it, you need to figure out which bits need to be changed so that you're dealing with new addresses, new interface APIs, things like that, and make those changes, compile it, test it, run it on the new platform. Now, the drawback of that is that you're making modifications to your code without adding any value. You're simply taking working code, moving it to a new device, and having working code. This takes time, which means it costs money. And the problem is that it's also error-prone. If you're making changes to reflect a new hardware platform, you may make a change which is not quite right, and so you might introduce errors that you didn't have before. Now with Java, the great thing is that you have this wonderful phrase that we've had right from the very beginning, which is write once, run anywhere. The reason for that is that we use a Java virtual machine. So the Java virtual machine gets ported to your hardware platform once and once only. Once that's been ported to the hardware platform, your application code runs unchanged. You use the same libraries, you use the same set of standard APIs, and you can run your code without any changes. You don't even need to recompile it because it's bytecodes. Bytecodes are a set of codes which work with this virtual machine rather than a real specific machine. And it's the JVM which converts from the bytecodes into the native instructions, the operating system calls that are required to make your code run. Now, a lot of people think about this and they say, well, you know, this interpreting actually makes the code run slowly compared to native code. And in the early days of Java, that was definitely the case because you were interpreting the bytecodes, you had to convert them to the native instructions, and so it did run slower than natively compiled code. However, because Java's 22, nearly 23 years old, a lot of work has gone into making that problem go away. So we now have what's called just-in-time compilation, adaptive compilation. You start with your bytecodes, you interpret those, and then the virtual machine will identify where you have loops, where you have specific methods that are being called again and again, where you have hotspots in your code. And it will then compile those bytecodes into native instructions. It will cache them so that the next time you come through the loop, you use the pre-compiled code rather than having to do the interpreting. And we'll talk a bit more about this later on, but the idea of just-in-time compilation can allow us to have better performance than with static compilation in many cases. So there are situations where we can actually get better performance using adaptive compilation than if we statically compiled our code. Reliability. This is a big one because obviously if we're going to deploy lots of things into the field, we need to make sure that they're going to work. And because this is the Internet of Things, it's not just going to be a data center. We could have things in a field, we could have things in a factory, we could have things where it's very difficult to get to them. So we need this code to be reliable so we don't have to go and change things by hand. One of the biggest problems that you have with using traditional ways of coding, things like C and C++, is that you are responsible as a developer for memory management. So this means that when you want to allocate space for something, in C you use malloc, in C++, you instantiate a new object. But then you, as a developer, have to remember to deallocate the space that's been assigned to those objects, or in C, the space that you're using. If you don't deallocate that space, you end up with a traditional memory leak. So you keep allocating space, you don't free it up, and then eventually you run out of memory. So that introduces a problem of reliability, because if you keep running for long enough, you run out of memory, your application can't continue, it stops. The other thing that's very important is you have to deallocate the right memory. So in C, you have a pointer to an area of memory. If you say, I want to free this particular pointer, the pointer is wrong. Let's say you say pass the value 0, which is quite common, then you'll get a segmentation fault and your code will stop abruptly. So again, reliability becomes an issue. Java solves this. So again, we have the solution of the Java virtual machine. Java virtual machine allocates space for us automatically. We can create objects simply by instantiating them with the new operator. But once we've done that, we don't have to worry about freeing up that space. Once we don't have any references to those objects in our code, the garbage collector, part of the JVM, will come through and it will say, that space isn't required anymore by your code, you don't have a reference to it, so you can't use it, we'll reclaim that space automatically. And again, we'll talk a little bit more about garbage collection and some of the advantages that we can do in terms of tuning that a little bit later on. Security. Security is an absolutely critical thing for any IoT type of application. If we're going to have sensors and actuators, gateways connected to a network, potentially a public network, the internet, then we need to be very careful about making sure that these devices can't be subverted, that people can't install malicious code. Great example of that is the worm that was used some time ago called Stuxnet, which was designed specifically for industrial type of devices and was used to try and create havoc with different things. One of the favorite ways that people use to create that kind of subversion of the code is through buffer overruns. So you say, okay, I've got an array of a particular size, but in C or C++, I can index off the end of that array, and I can go to memory which contains something which might be enable me to overwrite that and change what the application code can do. So you can do that through a number of different ways, but buffer overruns are a very commonly used attack vector. In Java, we don't have those problems. So Java was designed right from the very beginning to have secure code. It was designed right from the very beginning to be used in a distributed networked environment. So there's lots of things that happen in terms of Java that prevent you from installing malicious code. For example, when you load a class, the class bytecodes have to go through a 4-stage verification process by the JVM in order to assure the JVM that they are valid and can be executed. So you can't even handcraft bytecodes to try and subvert the JVM. Java doesn't use explicit pointers. So when you're dealing with a pointer to an object, it's an implicit pointer to that object. There's no actual number that you can manipulate. So you can't change the address of that object that you're referencing by adding something to it. It just doesn't work that way. So it's actually impossible to use a buffer overrun in Java because you simply can't index off the end of an array. We get an index array out exception. Skilled developers. Okay, so we've talked a bit about some of the ways that we need to protect our code and some of the easier ways that we can develop code. But having developers can be an issue. So traditional embedded development, gateway development requires special skills. Those special skills can be hard to find, and once you've found people with those skills, it can be hard to retain them afterwards. Java solves that problem. So the Java language, the Java platform, what you'll find is that most universities teach Java as a programming language. So it's actually very easy to find programmers straight out of university who know how to use Java. If you ask people like Oracle, who are the custodian of Java, they will tell you that there are 9 million Java developers worldwide. Now, not quite sure that that's a true number, but I think it's justifiable to say that there are certainly millions of Java developers worldwide. So it's relatively easy to find Java developers. The other thing is that when you're dealing with this idea of moving from the edge to the cloud, it's the same basic skill set across all of those things. You can take a Java developer, you can say, right, I want you to write a piece of code that will talk to this particular device using this library. Send these bytes, read these bytes. That's the same basic set of code skills as writing an application in the cloud, which is going to take that information, process it, store it in a database, and so on. So you can use those basic set of skills, add on things to that, and find the right kind of staff. So it's much easier to find the right kind of staff and skilled staff using Java than it is traditional embedded development. Tooling. Tooling is also a great way to help people develop code. So again, if you look at traditional embedded development, these tend to lack really good productivity tools. You tend to end up with command line interfaces, you end up with tool chains, you end up with all sorts of complex things that you need to do to compile and build your code. In terms of Java, there's lots of tools available, and that's right the way across from the idea of your IDE all the way through from continuous integration, continuous deployment, and these types of things. There's lots of different tools that are available for code management, team management, all those types of things. And pretty much all of these are available in an open source free version. So you've got 3 different IDEs that you can choose from: IntelliJ, NetBeans, and Eclipse, all of which have an open source free version. Then you've got build environments like Gradle, you've got Maven, you've got continuous integration and deployment through things like Jenkins. Again, all available for free. So there's no cost associated with that. And they're supported by a large number of developers, so things work very well with these kind of tools. Parallel processing. If you look at Moore's law, as I said, the density of transistors has increased every 24 months, doubling. What that's led to is not just that we have more complex processors, but because of the physical limitations of the clock speed and the power that needs to be provided to the processor and the heat that needs to be dissipated, what we now see is the increase in the number of cores, the number of processing units that we have on a single die, a single chip. So this means that it's now actually possible to do things in parallel. It used to be that we used a time-sharing operating system that made it look like we were doing things in parallel, but now we really can. Pretty much any processor you get these days will have multiple cores in it. What this means is that you need to be able to write multi-threaded code, and writing multi-threaded code is notoriously hard. If you look at things like C, C still doesn't have multi-threading built into the language. It's not part of the standard. You need things like pthreads, you need the POSIX threads library in order to be able to do that. C++ finally caught up with multi-threading. C++ from 2011 actually has threading built into it, but it's still at a very low level. If we look at Java, Java had multi-threading right from the very beginning. So if you look at Java version 1.0, there is a thread class, there's a runnable interface, there is synchronization that you can apply to methods, you can apply it to blocks of code so that you can have locking automatically applied for you, and there are methods in the thread interface or thread class which allow you to coordinate different threads by doing sleep, wait, interrupt, and notify. So that was a good start, but Java hasn't stood still. Java has continued to add lots of new features from a point of view of multi-threading. So if we're trying to develop multi-threaded code to use those multiple cores, it's a lot easier in Java. Way back in JDK 5, there was the concurrency utilities that introduced things like the semaphore, the atomic operations on objects. It introduced things like read-write locks, mutex. It's higher level things that people who wanted to write multi-threaded code were already familiar with. Then in Java SE 7, along came the fork join framework. Much simpler way of taking a large task that could be broken down into subtasks that can happen recursively until you get a small enough task to allocate to a single thread. Framework deals with all of that hard work of allocating a pool of threads, allocating queues to those threads, jobs to the queues, gathering all the results, and producing the result at the end. And then in JDK 8, we've seen the introduction of parallel streams so that we can simplify the way that we process code even further and make it much easier for us to deal with that kind of thing. So certainly from a parallel processing point of view, using Java is way, way simpler than using C or C++. Remote management. Again, this is the sort of thing where if you're deploying devices into the field and they're going to be in a factory, a shop, a house, a chemical plant, where they're difficult to get to, you need to be able to manage those devices remotely. You need to be able to update those devices with new services, new bug fixes maybe, things like that, but being able to do it remotely without having to visit every single device. So these are the sort of things that are hard to do. And again, Java provides us with a solution. There's things like Java MX, JMX, the Java management extensions. And then there's a nice set of APIs and framework called OSGI. Now, OSGI is a sort of module system, but it allows us to deploy new services remotely. So what we can do is we can create OSGI bundles. We can then deploy those onto a remote Java virtual machine and have that new service start up automatically. So it's a really simple way of being able to deploy new services onto our remote devices. JMX allows us to manage things. We can set up management beans so that we can monitor specific things. We can build specific beans for specific purposes and have different things monitored. So we're not restricted to only a set that's available with the JDK. We can build our own and extend those. Big data. How do we handle big data? So let's kind of look more at the cloud rather than at the edge. And when we deal with this, we need a different approach because we're dealing with potentially, gigabytes, terabytes, petabytes of data. How do we deal with that? How do we analyze that kind of data? How do we store it? How do we deal with the issue of clustering? Because what we're going to want to be able to do is have a number of machines clustered together and enable us to process all of this data. So again, Java provides a great set of solutions here because there are this wonderful set of open source frameworks that we can choose from that allow us to do all the sorts of things that we need in terms of big data. So you've got things like Hadoop, you've got things like Cassandra. So this is the idea of a database, distributed database that we can store information in. NoSQL databases, those types of things. So we're not restricted just to the traditional way of doing things with a traditional RDMS, Relational Database Management System, yeah. And then there's other tools. There's things like Spark for streaming data, Solar. There's also Spring XD, which has been designed for large amounts of data and big data type projects. So the great thing is that these are open source projects. A lot of them are run by Apache, so you can just download the code, you can download binaries, you can integrate them into your project. It doesn't cost anything. And again, lots of people know how to use these things because they've become very popular. Performance. So what we need to think about here is, okay, if we're going to run application code on our edge devices or in the cloud, because we still need to think about how much resources we need to use for this, what we need to think is how do we work in that type of environment? We've got to, in the edge, we've got constrained resources. We have less processing power, less memory, and so on. And as I said before, static compilation doesn't always equal better performance. So if we look at things like Java and the JVM, this again was designed right from the very beginning to be used in embedded applications. If you go way back to the very beginning of Java, it was designed to be used on a thing called the Star 7, which was literally the very first PDA. Designed to be embedded applications, it was designed to run in constrained environments. So JDK 1.0 would run in 8 megabytes of memory, and it would run at a reasonable speed there. Obviously, we've got a lot of development since then in terms of adaptive compilation, optimizing performance, and so on. Garbage collection has improved. So we can get very good performance from Java, even in constrained devices, because it has been designed right from the very beginning to work in those environments. So we've talked about the challenges, we've talked about the solutions. Let's talk a little bit about Azul, the JVM company, because how do we look at solutions using Java? What solutions are available to us? So Azul, as a company, only does one thing. We do JVMs, and we really have, if you like, 3 different products. There's what's called Zing, there's what's called Zulu Enterprise, and Zulu Embedded. So if we look at Zulu for Embedded, what this is we take the OpenJDK source code, Now, OpenJDK is the open source reference implementation for the JDK. It's the reference implementation for the Java SE standard that's defined by the Java community process through specific JSRs. What we do is we take that, we build it into binary distributions, and that will pass all of the TCK tests. So there's the technology compatibility kit, which guarantees that everything in that binary distribution conforms to the Java standard. So you know that your code will run on that. We have ports for Intel, we have ports for ARM, we have ports for PowerPC. So we cover a range of different processors. If we look specifically at the ARM architecture, we cover v6, v7, and more recently v8. Both soft and hard float are available. This becomes an issue when dealing with the specific architecture using for the processor. And we recently released, a couple of months ago, the full 64-bit version for ARM. So we have both 32 and 64-bit versions available. And what we've also done is some work around the way that the compiler, the internal JIT compiler, works for that. So there are two compilers, C1 and C2, sometimes called the client and the server compiler. And we've done a lot of work to improve the way that works, specifically for embedded devices. This is a drop-in replacement for other JVMs. So it is just a JVM. It's exactly the same as other JVMs built from the OpenJDK in terms of the interfaces. And so you don't have to worry about porting your code, modifying your code to work with it. And the nice thing about this is it doesn't have licensing restrictions. It's built from OpenJDK, it's built from open source, and so what are called the field of use restrictions that you will see with other JVMs do not apply to Zulu Java for Embedded. Zulu for Enterprise is more the sort of traditional binary distribution that we create specifically for desktops or for the cloud. So again, it's 100% open source build of OpenJDK. It passes all the TCK tests, free for download, free for use. What we then do is we can provide commercial support on top of that. So it's free for use if you want to, but if you want support, we can do that as well. So we can discuss that with you if you're interested. As I say, we provide the standard set of binaries there. So we have a Windows version, we have a Linux version, and we have a Mac version. We also support older versions of Java. So we go back to JDK 6, we have JDK 7, and we have the current JDK 8. Because JDK 9 will be out literally in 2 weeks' time, we have JDK 9 early access available. And what we do is we take the security fixes that we get for JDK 8 and we backport those to 7 and 6. And if you are a commercial support customer for us and you have a problem which is not being fixed by one of the patches or the security fixes, we can fix those as well. So we're not just applying patches from somebody else, we're actually able to fix problems as well. It's all ready for cloud, it's all ready for virtualization, so we have support for Amazon Web Services, we have support for Microsoft Azure, and we have Docker containers that this will run in as well. If you're looking at the cloud and you want better performance, then we have Zing. Zing is our commercial JVM. This replaces some of the things that you see in the OpenJDK implementation with better performing versions. So we replace the garbage collector with a thing called C4, the continuous compacting concurrent collector. What this allows us to do is have ultra low pauses, very, very low pauses of the order of a few milliseconds rather than a few seconds, regardless of how big your heap is. And the heap will scale currently all the way from 1 gigabyte up to 2 terabytes. Now, it doesn't mean you need 2 terabytes, but if you want to scale all the way up to that, you can. And we're currently working on bigger heaps for the future. The other thing we've done more recently is to replace part of the JIT compiler in the OpenJDK source code. So rather than having the C2 server compiler, we have our own version called Falcon. And Falcon is the fastest animal on the planet. So we thought we would call our compiler Falcon because it's the fastest compiler on the planet. This is based on an open source project called LLVM, and it's a rewrite of this particular part of the compiler. What it allows us to do is to take advantage of modern CPU architectures. So if you look at some of the most recent Intel architectures, they have vectorization instructions built in. So there's a thing called AVX, there's AVX2, and most recent is AVX512. So you have very wide registers up to 512 bits, that will allow you to do single instruction, multiple data operations on that. And by using AlGIT, we can actually take advantage of that in more situations than you would with the older compiler. The other thing we do is look at how to solve the problem of warm-up, because when you start your application, it will be interpreted until the hotspots are identified and the code is compiled. What we do is, rather than doing ahead of time compilation, we store a profile once your application has been running for a while, and that profile identifies which classes need to be loaded, which methods need to be compiled. That way we can do that before your application starts running. So we will do that compilation and that loading before you get to your main method in your application code. By using this profile, we can get much better performance very quickly and less what are called de-optimizations. So here's an example just to put this into context. This is Zing running a Cassandra node. So this is a cloud type of environment. And on the left, what we're seeing is the latency associated with the Cassandra example running on a hotspot virtual machine. You can see there's lots of red on there, and what we're measuring is the latency, so how long it takes to respond to a request. And if you look at that graph on the left, what you'll see is that we're seeing a sort of fairly continuous pause of around 200 milliseconds with a spike that goes all the way up to about 1 1/3 seconds. I've actually scaled the graph the same both on the left and the right, which does make it a little bit difficult to see what Zing is doing, because Zing is basically just a flat line at the bottom. What we're really seeing, you can just about see at the bottom there, is a maximum pause of 10 milliseconds. That's a maximum pause. Rather than a maximum pause of 1400 milliseconds, maximum pause of 10 milliseconds. So this gives you an idea of what Zing can do in terms of improving performance for a typical example of something like Cassandra. So to kind of put that into perspective, this is what you see typically in terms of performance for a traditional JVM. The graph in this case is showing the level of performance. This is not latency, it's how well the JVM is performing with your application code. So you'll see that at the beginning we're seeing interpreted bytecodes, then we're getting into the C1 compiler, which is in green, then we get into the C2 compiler, which is in blue, and it gradually warms up. We're seeing dips in performance. Those are the little sort of dips that you see from time to time, firstly for de-optimizations for the compiler, and then once it's reached a steady state, we're still seeing that for garbage collection. If we see how that works in terms of Zing, what we'll see is that. So we shift the graph so that rather than having a lot of time to warm up, Ready Now will shift everything so we have a much faster warm up. We reload the profile, we reload the necessary classes, we recompile the necessary methods. We eliminate a lot of these de-optimizations because we know what the profile is and we can do that. Falcon will push the level of performance higher. So we're getting better performance from our application code, so we're getting overall better performance. And C4, the different garbage collector, will eliminate these dips in performance. So we get a much smoother, much nicer looking profile for the performance of your application when it's running on Zing. Just to summarize, in terms of conclusions, Java is an ideal solution for all the tiers of IoT, so our edge devices, our gateways, and our cloud. It solves the problems that I've explained, from security, parallel processing, access to staff, libraries, tooling, all of those different things. Makes development a lot easier, makes it quicker, makes it cheaper. The fact that you can go from the edge to the cloud using Java also makes it easier to design the architecture of your application because you're using the same set of technologies across the whole thing. We can deliver superior performance from the edge to the cloud. And if we look at the different things that you can get from Azul, you've got Zulu for embedded devices, Zulu for enterprise, gives you simpler licensing, simpler support. And then for the cloud, if you want Zing for superior performance and scalability. If you want to get started, we can help you with that. In terms of Zing, you can get a 30-day free trial. Go to azul.com/Zing trial. You can download Zing and you can try it free for 30 days. If you want some help with that, we'll be very happy to have our engineers work with you to see what we can do to improve performance. But typically, Zing works really well straight out of the box. There's none of this complicated tuning. You simply say, set my heap to be this size, and off you go. For Zulu, there are free downloads that you can go to zulu.org/download for, and you can either download Zulu for Mac, Windows, or Linux, or you can download the embedded versions as well. And as I say, those are free. If you're interested in talking to us about commercial contracts for those, then we will be happy to discuss that with you at some other time. So that is basically all I have for today. So thank you very much. What I'm going to do now is I'm just going to see if there are any questions. So I'll go to questions, see if we've got anything there. Okay. So I have one question here, which is, could you clarify the licensing in terms of field of use? Yes. So what I mean by this is that if you look at the JVM that's available from Oracle, it's based on OpenJDK, but it has a field of use restriction associated with it. That means that if you want to use Java on an embedded device, and an embedded device is anything which has a single purpose, so it doesn't mean it has to be a small device. If you're building something like a kiosk for an airport or a supermarket, something like that, that counts as an embedded device. So that means that the field of use restriction means you can't just use Java for free. You have to pay Oracle a licensing fee for that. If you want to use Zulu for embedded, it doesn't have that. It's built on OpenJDK. There's no field of use restriction, so you're not required to pay a license fee for it. We will help you with support, but you don't have to pay a licensing fee for it. So that's what I mean by the field of use restriction and the licensing being different to the way that other people license their code. I think that's it. So if you have other questions, please feel free to, you can reach me on Twitter. My Twitter handle is SpeakJava, so if there's anything else you want answered, please do feel free to reach out to me on there. With that, thank you very much.